And these are all the things that we have seen so far, and we have to start somewhere from here. And you can see there can be compounds without asymmetric carbon and be optically active. It is possible. See, up to +2 level, you might have studied that the optical activity is just because of the asymmetry. But some compounds are called biphenyls, spiranes, allenes. These compounds also show optical activity, and it is not because of asymmetry, it is because of dissymmetry. So it's because of dissymmetry. So molecular dissymmetry, it is due to the bulky atoms or groups, and the presence of the bulky atoms or groups, they make the compound non-planar, and also the compounds experience a hindered rotation, and the optical isomerism due to the restricted rotation in ortho-substituted biphenyls and other allenes. It is called atrope isomerism. You look at this compound. This is allene. A carbon here double bonded to another carbon, which is again double bonded to another carbon. And here is a Cl and here is a H. And look at here, this dark bonds. This indicates that the chlorine is projecting towards the viewer and the hydrogen is away from the viewer, whereas these two, hydrogen and chlorine, are in the plane of your screen. They are on the plane of your screen. You can understand the structure of the allene only when you look into actual allene model. Probably in the next class, I will show you the actual structure of allene. And also here also this ring is, actually it is projecting towards the viewer. And see here, it is also projecting towards the viewer. And this is a biphenyl structure. When it is ortho-substituted, what will happen? It is a bulky group, and this is also a group, and here it is a bulky group. Therefore, these two groups cannot be present in a plane. So what will happen? They will repel each other because of the steric hindrance. So this ring is perpendicular to the plane of the screen, whereas this ring is existing in the plane of the screen. So this single bond, actually it is free to rotate, but the rotation is restricted. It is restricted because of the bulky groups present. And this restricted rotation makes the dissymmetry. And because of this, the compounds become optically active, and which is called atrope isomerism. So this is about the dissymmetry. Now look, what is optical activity? See, suppose the light radiation is coming from your screen, that is perpendicular to your screen is the direction of a propagation of the light wave. In a transverse wave, the vibrations will be perpendicular to the direction of propagation of the wave. So for this particular line which passes through the center where I am putting my mouse, marking, it is at this point in a perpendicular direction, the light is propagating. So it can have innumerable number of perpendiculars. This is one perpendicular, this is one perpendicular, this is one perpendicular, this is one perpendicular. I have just mentioned some 8 perpendiculars. But actually speaking, a straight line can have infinite number of perpendiculars. So a light wave is a transverse wave. Transverse wave means the vibration of the wave will be perpendicular to the direction of propagation of the wave. So this vibration can be in all the perpendicular planes. So an unpolarized light has the vibrations in all the perpendicular planes which are perpendicular to the direction of a propagation of the wave. When this unpolarized light is passed through a device called a polarizer, it is called a nickel prism, which is island bar, spar, which is a calcium carbonate. Actually, this calcium carbonate crystal is having, when it is mixed with one more type of spar, you are making up the nickel prism. And this nickel prism has very small slit, so that the vibrations in all other planes will be cut off, and the vibration in only one plane will be permitted to go through the very fine or very small slit. This is how a light is a plane polarized. Look here, this is the unpolarized light having the vibrations in all the perpendicular planes. Whereas this is the plane polarized light where the vibration is restricted to only one plane, which is also perpendicular to the direction of propagation of the wave, but which is perpendicular to the direction of propagation of the wave, but it is confined to only one plane. Right. And another device called a polarimeter. When you are viewing this one particular plane polarized light through the polarimeter, you can wind the polarimeter slit direction, and you can note down the point at which you are getting the maximum intensity, where that is the plane in which the vibration is coming. So what is this optical activity? When a plane polarized light is passed through a solution containing optically active compound, the plane of the plane polarized light is inclined either towards right or towards left. And the angle of inclination of the plane polarized light is called alpha. If it is towards the right direction, it is called dextrorotatory, or the angle is given a sign positive. If it is towards the left, it is called levorotatory L, which is given the sign minus. So this entire mechanism you should understand. First of all, you should understand what is an unpolarized light and what is a plane polarized light. Unpolarized light has vibrations in all the planes which are perpendicular to the direction of propagation of the light. And the plane polarized light is having the vibration in only one plane. How a plane polarized light is cast, it is made when the unpolarized light is passed through a nickel prism. The nickel prism has a slit very small, so the vibrations in all other planes are cut off, and the light which is coming out of the nickel prism will have the vibration in only one form, in only one plane. So what happens? When that plane polarized light is passed through a solution containing the optically active substance, the plane of the plane polarized light is inclined either towards right or towards left. If it is inclined towards right, it is called a dextrorotatory, which is given a positive sign before the degree of its inclination. And if it is inclined towards left, it is called a levo-rotatory, where a sign of a minus is given before the angle of inclination. And this is the entire setup. Look here. First of all, it is an unpolarized light, which is passing through a polarizer. And what is coming out is a plain polarized light. And there is another cylindrical transparent tube, which contains the sample solution. And then when the light is coming out of this, it is turned either towards right or towards left. And then its turning is found out using another device called the polarimeter, where you can wind and change the, the polarimeter eyepiece, and you can find out the place at which you are getting the maximum intensity of the light. And then there will be marking by which originally the light is supposed to come in this line, and now after you are turning, it is coming here in this line. Therefore, you can, there itself, you can measure the angle of the inclination, angle of the turn, which the plane polarized light has experienced. But this is called alpha. If alpha is positive, then the substance is called dextrorotatory. If the alpha is negative, it is called levorotatory. And this alpha depends upon, it depends upon five factors. First factor is the concentration. If we have a high concentration of the substance, then the alpha will be more. And also, alpha depends upon the light path through the solution. So you can also adjust the length of the sample tube. Suppose the sample tube is lengthier, then the light has to travel a long distance inside this tube. So consequently through the solution. So it is the light path through the solution. And also the temperature. Temperature is also a very important factor which affects the polarization. And wavelength of the light used. When you change the wavelength of the light, what is wavelength? Wavelength is the distance between any two successive points in the wave which are in the same state of vibration. And also, alpha depends upon the solvent. So here, you have to calculate the specific rotation. Specific means you can change the concentration, you can change the length, and depending upon the length and the concentration, the alpha changes. But you should develop a formula to calculate the rotation of the plane polarized light either towards right or left when the length is unit and the concentration is also unit. For a unit length and a unit concentration, what will be the rotation? That is called the specific rotation. So specific rotation is mentioned like this: alpha within a square bracket d 20. 20 means it is measured at 20 degrees centigrade. So this alpha d20 is equal to alpha divided by length into concentration. So here the length, if length is mentioned in meter, then you have to mention the concentration in mole per meter cube. If it is mentioned in the mole per decimeter cube, that is mole per liter, then the length should also be mentioned in decimeter. So unit conversions are very important in chemical calculations. So if you want to measure alpha from the specific rotation, the rotation is equal to specific rotation into length into concentration. So this is the relation between rotation and the specific rotation of the plane polarized light. Next. Look here. You have to understand another thing called molecular rotation. What is this molecular rotation? Molecular rotation is specific rotation multiplied by molecular weight divided by 100. This is called a molecular rotation. And I have already explained What is dextrorotatory substance and what is levorotatory substance? Dextrorotatory substance means it turns the plane of the plane polarized light towards the right. Levorotatory substance, it turns the plane of the plane polarized light towards left. You are taking a compound which has two compounds which have similar molecular formula and their chemical and physical properties are identical, but when the light is passed through solution of one substance, the light is the plane of the plane polarized turns towards right direction, and in the solution of the other substance it turns towards left direction. But the relation between these two substances is the mirror images. Then these two substances are called optical isomers. And if these optical isomers are non-superimposable mirror images, they are called enantiomers. But they are having identical Grass structure. They have the same molecular formula and also identical Grass structure. But they are non-superimposable mirror images, and also they are optical isomers. And optical isomers, which are non-superimposable mirror images with the same molecular formula and the identical Grass structure, they are called enantiomers. So now we are going to discuss the properties of enantiomers. First property, they have identical physical properties and they differ only in optical rotation. Sometimes dextrorotatory, sometimes levorotatory, and D and L can also be represented as plus or minus. And also they have identical chemical properties except their action towards optically active reagent. This particular point you should understand very well. I'm going to take this one. See, this is secondary butyl alcohol. So alcohol, the OH group is connected to the second carbon. See, 1, 2, 3, 4. So I can write this is a 2-butanol. So when this is a 2-butanol, when it reacts with sulfuric acid, it absorbs water molecule. So what you are getting is a double bond between the first carbon and the second carbon. See, you are getting butene, 1 butene. So 1, 2, 3, 4, 1 butene you are getting. When the same compound reacts with HBr, you are getting 2-bromobutane. 2-bromobutane. So when it is reacting with acetic acid, correspondingly you are getting the acetate, butyl acetate. But see, the acetic acid addition has taken place in the OH group. See, OH and this acid group, they have combined, and what you have got is an ester. Why these three reactions are taken? See, this carbon is an asymmetric carbon. Suppose if you want to see this molecule in the Fischer projection, this OH group and this ethyl group, they are projecting towards the viewer, and this methyl group and the hydrogen are away from the viewer. You can assume a mirror image compound also. Suppose if this OH is on this side and the ethyl group is on this side, they are enantiomers, no doubt about it. They are enantiomers. They are not the same compound. They are isomers, because OH here it is on the right side. On the other compound, it will, if it is on the left hand side, even then you will not find any difference in this product formation. Whether the OH is here or here, what you are going to get will be 2-butene. What you are going to get will be 2-bromobutane. What you are going to get will be the substitution of the esterification at the second carbon. It is not going to change. That is what is mentioned here. They have identical chemical properties. They have similar physical properties. The density is the same, mass is the same, refractive index is the same, viscosity is the same, boiling point is the same, melting point is the same, density is the same. Everything is identical except the optical rotation. But when you think of the chemical properties, everything is identical. If you use very common reagents, which are non uh, optically active reagents, the product is going to be identical for both the enantiomers. The optical isomers will give you the same product with non-optically active reagents. But even then, even their products are identical and the rate of the reaction, they are also identical. The reaction rate, there will not be any change. Everything is identical. But if the reagent itself is optically active, suppose I take the secondary butyl alcohol plus form and I want to make it react with plus lactic acid. Next, I'm taking the plus isomer of the secondary butyl alcohol and I'm making it react with a minus lactic acid. Then what happens? The plus minus combination, the rate of the reaction is different from the minus minus combination, the rate of the reaction. So when the reagent also becomes optically active, when the reactant is optically active and I am taking a plus isomer and I am allowing it to react with a plus reagent, the reaction rate is different. When I take a plus isomer and the reagent is a minus, the reaction rate is entirely different. When I take a minus and a minus, again the reaction rate is different. So such reactions are called stereospecific reactions. Stereospecific. So if you are not taking optically active reagent, mere chemical reactions will be identical for both the enantiomers. Even the reaction rates will be the same, but there will be a difference when you are using optically active reagents. And the other property is, I'm not able to see the screen, what's there. Normally the biochemical reactions, all the biochemical reactions are stereospecific. Why they are stereospecific? Even in our body, a particular isomer will have more bioreactivity. Normally, when you are suffering from some allergy or allergic cough or something, you may be very familiar that the doctors will prescribe cetirizine. Cetirizine is a normal antihistamine compound. Cetirizine. Many of you may be having the experience of taking cetirizine. Even that cetirizine, dextrocetirizine is there, levocetirizine is there. When you take a normal cetirizine, you will feel more sleepy. But when you take a levocetirizine, the sleepy nature or the tendency to be sleepy will be considerably reduced because our biochemical system, it responds in different manners for different optical isomers, for different enantiomers. So if you take glucose, glucose is also an optically active compound. Suppose if you take that one particular carbon connected to aldehyde group, hydrogen, OH, and then the rest of the skeleton, that carbon is optically active. And you can even think of the same carbon in the mirror image form. So in such conditions, you can have two types of glucose molecules. One is plus glucose and another one is minus glucose. You know one thing, the yeast, which is able to ferment and metabolize glucose, will metabolize only plus glucose. The minus glucose cannot be metabolized, cannot be fermented by the yeast. See, biochemical reactions are stereospecific. So enantiomers have different biochemical properties. Why these reaction rates for enantiomers with optically active reagents are found to be different? When you think of the transition states, you should understand what is a transition state. Transition state means, see, suppose you take two substances A and B, they combine to give a product C, and before forming the product, they form a transition state, a short-lived, a highly reactive, a combined state is called a transition state. And in the transition state, we are getting a AB complex, both combined together. And then the next step is to get themselves converted into the product C. So what will happen when you are taking enantiomeric substances and optically active reagents? Different energy of activation is found for different combinations. You take a plus secondary butyl alcohol and plus lactic acid, the energy of activation is different. If you take a plus secondary butyl alcohol and minus lactic acid, the energy of activation is different. And because of the differences between the energy of activation, the reaction rates are also different. So this is of actually the enantiomers respond to optically active reagents. The main point that you have to understand here is all the biological reactions are highly stereospecific. And the next concept is racemic modification. What is this racemic modification? You should understand what is a racemic mixture. Racemic mixture means a mixture of equal parts of enantiomers. It is called a racemic modification or racemic mixture. Suppose I have 50 molecules of plus lactic acid and 50 molecules of minus lactic acid, and I put together, what will happen? The 50 molecules of a plus lactic acid will try to turn the plane of the plane polarized light towards right, and the 50 other molecules of minus lactic acid will try to turn the plane of the plane polarized light towards the left to the same extent. As a result, the light will come out unaffected. There won't be any change in the direction of the plane. You may not observe any inclination either towards right or towards left. So the plane polarized light is not experiencing any change when it passes through a solution containing equal parts of enantiomers. This is called external compensation. So the light turnings are compensated externally. Why it is externally? One molecule turns it towards right and the other molecule turns it towards left. They are externally compensated. Then you should understand there is internal compensation also. Say for example, if you take mesotartaric acid. Mesotartaric acid, there are two asymmetric carbons. One carbon turns towards right and another carbon turns the plane polarized light towards left. But these opposite turnings are found within the molecule itself. One single molecule is having two centers, and one center is dextroactive and the other center is levoactive. This type of cancellation of the turning of the plane polarized light is called internal compensation. But what we are seeing here in the racemic modification is external compensation. So the mixture of equal parts of the enantiomers is denoted as plus or minus put together in a bracket, or BL, both written together. So actually these racemic mixtures are synthesized when a chiral compound is synthesized from a chiral compound. For example, you are taking this propionic acid. See, In the propionic acid, it is a chiral compound. Why it is an achiral compound? The carbon, which is denoted in this diagram, which is presented here. One side it is connected to methyl group, and the other side it is connected to the acid group, carboxylic group, and the carbon has two more hydrogens. So it cannot be called an asymmetric center because all the four groups attached to this carbon are not different. There are two hydrogens. Now I am brominating this propionic acid. So the bromination can take place. The probability of substitution to take place in this position and in this position are the same. So bromine is trying to replace a hydrogen connected to the carbon. So the bromine can remove this hydrogen and also bromine can remove this hydrogen. And what is the probability of replacing the hydrogen on the right and the hydrogen on the left? They are equally probable. And because of this equal probability, when the reaction is completed, you will be getting more or less equal number of compounds in which in one compound, bromine is substituted on the right hand side. In other compound, it is substituted in the left hand side. Now, this particular compound is asymmetric because methyl group, bromine, carboxylic group, hydrogen, four different groups are attached to this carbon. And this carbon is also asymmetric. Four different groups are attached to this carbon. But these two things are mirror images. And also because of the equal probability, more or less the same quantity of these two substances would have been resulted. And the product what you have got is a racemic mixture, which is as a whole optically inactive because the external compensation. Because of the external compensation, these two compounds put together, they are optically inactive. Now look here. Normally, it is not possible to separate the enantiomers from the racemic mixture because they have the same melting point, the same boiling point, and the same solubility. It is not at all possible to separate them. But special methods are available. The separation of the racemic mixture into enantiomers is called resolution. The racemic mixture is optically inactive due to external compensation. Sometimes, if one enantiomer goes excess, then the mixture will have a resultant optical rotation, which is mentioned as enantiometric excess, EE. If you take a pure enantiomer, that is, which has only one compound, a pure enantiomer, then the enantiometric excess is called 100% here. Now the meeting is going